Okay. Hello, this is the CUDAN Open Lab seminar for Cultural Data Analytics on April 7, 2025. And today it is our greatest pleasure to have Karl Friston from UCL London, who will speak about the physics of communication, which has to do with brain and culture and cognition. And we're very happy to hear Karl talk. Karl, the stage is yours.
Well, thank you very much. It's a great pleasure to be able to speak to you. I should apologize. I'm doing a very, very simple kind of communication. So I'm going to focus on what it means to engage, couple, or synchronize with your lived world through the lens of physics. So I'm going to focus on a very elemental kind of communication, specifically the notion of generalized synchronization between a correspondent and the person who is listening to her. So my talk's going to be predicated very much upon the work of Helmholtz. I've extracted this particular quote from Helmholtz that seemed prescient for communication. I'll just read it out and then we'll come back to it at the end. And my hope is that after the presentation, this will make a lot more sense. So, no perception obtained by the senses are merely sensations impressed upon our nervous system. A peculiar intellectual activity is required to pass from a nervous sensation to the conception of an external object, which the sensation has aroused. The sensations of our nerves of sense are mere symbols, indicating certain external objects, and it is usually only after considerable practice that we acquire the power of drawing correct conclusions from our sensations respecting the corresponding objects. So that was a rather long-winded, if fluent, description of his notion of unconscious inference, which underwrites much of what I want to communicate and hopefully discuss with you afterwards. However, I'm going to sort of put that perspective on hold for a moment, and for the first half of the talk, I'm going to talk about the physics of self-organization, and in particular, the kind of self-organization associated with sentient systems or creatures, with a special emphasis on something called Markov blankets and the Bayesian mechanics that ensue. So this is a story that a physicist would tell when trying to understand self-organization or particular things that are open to their environment, either in the sense that the environment supplies sensory input or information, and crucially, the system or the agent can act back upon that environment. Then we'll come back to Helmholtz and talk about the anatomy of inference in the brain, with a particular focus on predictive coding formulations on neural networks, and then use that predictive coding perspective just to illustrate a very elemental kind of communication using Birdsong and synchronization of chaos. So that's the roadmap. I do tend to talk a lot, so please interrupt me when I'm getting towards the end, because usually I find the questions and answers are more illuminating than me going through the material. However, let's just start with a question posed by Schrödinger. How can the events in space and time which take place within the spatial boundary of a living organism be accounted for by physics and chemistry? And what I want to do is just focus on the notion of a boundary, noting that in order to talk about anything, a self, a particle, a person, or a population, we need to be able to separate or disambiguate that thing from everything else or nothing. And that separation I'm going to take or read as a Markov blanket, namely a statistical boundary that separates me from my world or my eco-niche or my heat bath. So what's a Markov blanket? I've tried to illustrate it for those people who don't know in terms of this little diagram down here, this graphical model where we can imagine the states of some universe being denoted by these little blue circles, and some states influence or cause changes in other states. And if I just identify one set of states, say my states, and call these states internal to me, they're inside me, then the Markov blanket comprises the children, the parents, and the parents of the children. So this set of states, which I repeat are the parents, the children, and the parents of the children, provide a set of states that effectively insulate me from the rest of the universe in a particular sense. And that sense is that if I wanted to know how my dynamics are going to evolve in the moment, I would only need to know the states of my Markov blanket in order to predict how I am going to change. In other words, the internal states are conditionally independent of these external states, given the Markov blanket states. I'm going to make a further move here. I'm going to partition the blanket states into something called sensory states that are not influenced by the internal states, and active states that are influenced by the internal states but do not influence the internal states. And with this particular partition, I've now got a description of a particle or person or a population in terms of their internal states enshrouded by these blanket states constituted by the sensory and active states, and these collectively can be regarded as the states of a particle or a particular states. I repeat, we can generalize this to anything that can be described or separated from their environment. Just to put more flesh or more substance on this partition, let's consider one of my favorite systems, namely the human brain. On that view, the internal states can be regarded as all the synaptic activities, efficacies, all the connections, all the states of a particular brain that I would need to list in order to define where I am in some abstract state space. And these would be the internal states. And these internal states influence the active states, say my actuators or my autonomic reflexes, that change states in the outside world, namely extrapersonal space or indeed my physical body. And then the changes in the external states out there beyond my Markov blanket reciprocate by causing changes in my sensory states, in my sensory epithelium, my eyes, or any sensory organs that then cause changes in my internal states. And so we establish, just by having this separation between the inside and the outside, a kind of action perception cycle, a circular causality where the inside influences the outside through action, through active states, and the outside influences the inside through sensations or sensory states. So what I want to do now is just ask you to forget about the Markov blanket for a short period of time. What we're going to do now is just do some very basic physics and then put the Markov blanket back into play again, and then to see what special kind of mechanics emerges just by the existence of a Markov blanket, or even more simply, the existence of something that can be separated from everything else. So the physics I want to do, please don't worry about the equations. I'll try and make this as intuitive as possible. The physics that I want to talk about is all reducible to dynamics, and I'm writing down dynamics here in the form of a Langevin equation. The rate of change of some states of the universe, denoted by the dot, is a lawful function of where I am in this state space, plus some random fluctuations. And I've cartooned that here in terms of two states. These could be two of my states at any particular scale. They could be oscillations in a cell in my brain, unfolding over a few hundred milliseconds or even less. It could be my cardiac cycle. It could be me getting up in the morning, doing my emails, having a cup of coffee, or it could be an annual cycle of Easter, summer holidays, Christmas, and the like. The key point about this dynamics is that I have to keep revisiting characteristic states that I was once in. technically, this is called a pullback attractor. The states that characterize me, given the kind of thing that I am, that it looks as if I'm attracted to, because I can't occupy other states. There are many, many more ways of not being me than there are being me. This trajectory, as I move through state space, has another interpretation. You could read this as the density of, or the probability density of finding me in a particular characteristic state of my attracting manifold if you sampled me at any one point in time. And I'm denoting that by the probability of being in this state given I am me. And that's a useful perspective because nearly all of physics rests upon the lawful evolution of this probability density here. I've written that down in terms of the Fokker-Planck equation. Other people might know this in terms of the Schrödinger wave equation, master equation in discrete systems, a very ubiquitous and a very powerful expression that if I know the flow and the amplitude of the random fluctuations, then I can work out how this probability distribution changes over time. However, I've just said that for something to exist with characteristic states, this probability distribution doesn't change with time because I am something that can be sustained in the sense that I keep revisiting those states. So I know that this rate of change of this probability density is zero. And that's really interesting because it means I can rearrange this part here to express my dynamics, my flow, the way that I change in terms of what's called a gradient flow on the logarithm of this probability density. And it has two parts. Intuitively, I can decompose all of my dynamics, all my flow through this state space into two parts. One, effectively ascending these log probability distributions, and the other one circulating around on the iso contours. And we'll all be familiar with this sort of flow if we think about water escaping from a bathtub. So the gradient flow, sometimes referred to as the dissipative flow, goes down the plug hole, whereas the conservative flow, the non-dissipative part, sometimes known as solenoidal flow, circulates around as the water is flowing down. And this is true of anything that has dynamics and has this can be described in terms of evolving probability distributions that have this non-equilibrium steady state. And I've just described that here in terms of the solenoidal flow, the conservative flow that could describe, for example, the circulation of heavenly bodies in our solar system, or it could describe life cycles or oscillations or biorhythms, and the gradient flow here, which is effectively gathering up the system so that the system is pulled towards this pullback attractor, countering the effect of the random fluctuations that tend to dissipate it, and that's why it's called a dissipative component.
So, what is Q here? What is Q and where it came from?
What is Q and where it came from is the question.
Right. The Q and the lambda inherit from something called the Helmholtz, or more technically, the Helmholtz-Hodge decomposition. And it comes from the fundamental lemma of variational calculus and arose in fluid dynamics. And it just says that if you've got, for example, a non-compressible liquid and there's a flow, you can always express that flow in terms of two orthogonal parts. One part depends upon the amplitude of the random fluctuations, and that drives the dissipative part. And then the other part, which is at right angles, is described by Q. So Q is an antisymmetric, effectively as antisymmetric matrix that just decomposes the flow into two orthogonal parts, one which is driven by gradients that depends upon the random fluctuations, and the other one that doesn't. So if you think about something that's circulating in orbit, as it's sufficiently large, then there are no random fluctuations, and the Q dominates over the dissipative part, and you get sort of orbital motion, for example. On the other hand, if something is very, very small, say at the quantum scale, then the random fluctuations dominate, and effectively you get sort of dissipative dynamics, and everything is trying to find its minima in the negative log probability or its maximum in the probability. Does that help?
Yes, reasonably.
Yeah, I have another question, maybe, which would be cool for clarity. So when you do this decomposition, like you say, you can do that because you put the probability to 0. Basically, what you're saying, if I understand right, that so as a human going from work to home and sort of having certain routines, I have a steady state space. While this is only true in the short run and in the short term. Like, are you like laying it out in a way where you say, okay, right now we're modeling sort of like humans that have a steady state space, while one could widen this whole model to actually take into account that there is actual a dynamics of the state space itself going on?
Yeah, that's an excellent question. So let me qualify. So we are, exactly as you're intimating, talking about non-equilibrium steady states, the steady states of open systems at a particular time scale. So for as long as these kinds of states characterize me, then this mathematics applies. However, you can deploy this in the context of the renormalization group to put a slower timescale on top, and then reapply exactly the same mathematics. So we're not saying that these characteristic states characterize anything for t equals infinity, but for some suitable time length over which this particular thing or configuration or person exists in these characteristic states, then this is an apt solution to their dynamics. So you get into really interesting arguments or derivations when applying the renormalization group to this. But you'd recapitulate this kind of thing at a much slower time scale and then do so recursively. So you're absolutely right. The very fact that you do have a routine, a daily routine, which is also a weekly routine, which you recurrently engage in for several years at a time, would mean that at that scale, at that coarse graining of that state space appropriate for that scale of self-organization, the period of time we're talking about could be several years, but it wouldn't apply at the point of your birth or as after you retire, for example. So that would then move to the next scale, which would be a life cycle. But there's a life cycle that exists in terms of at an evolutionary scale and in terms of characteristic states of being during a life scale, and then so on. You can just keep on reapplying this at the same level. Is that what you have in mind?
Thank you very much. Yeah. I think we should get back to that at the end, because otherwise I derail where you want to go. Like, just go ahead. Thank you very much.
Yes. Yeah, we're not going to finish this presentation, I can see already. That doesn't matter. This is much more interesting. So having established this sort of basic dynamics of effectively systems that are self-maintaining or self-organizing or self-sustaining over a non-trivial amount of time, what we can do now is ask, well, what about the Markov blanket? So under the qualifications that we've just discussed, those rules, that law, that Helmholtz decomposition applies to everything, including the partition that we introduced at the beginning. So it applies to the internal states and it applies to the active states. And I've just written it out again in terms of the dissipative and the non-dissipative or solenoidal parts of a gradient flow on the log probability. But now, in terms of the Markov blankets, or at least the sensory sectors of the Markov blankets, for the internal states and the active states. And the argument here is that this provides a mathematical image of some generalized notion of perception and action. And I just wanted to qualify that or substantiate that interpretation just by appeal to a lot of global formulations of self-organization and behavior and decision-making. If you recall, this probability here is just a way of scoring the kind of states that characterize me, that it looks as if I am attracted to, the kind of states I that are definitive of me as a sustainable particle or person. So they have value for me. So both action and perception on this reading will look as if they are in the service of maximizing value, in the sense that there is this gradient flow on this log probability. One can read that in terms of reinforcement learning. If you're an engineer, it would be optimal control theory. If you're an economist, you could read it as expected utility theory, where utility or value or negative loss or cost is just scored by the log of the probability that this state is on my attracting set. If I just put a minus sign in front of it, I get something that you would recognize in information theory as self-information, sometimes called surprisal, or more simply just surprise. And incidentally, this is what the free energy is referring to as a bound upon this surprisal or self-information. So these equations, this Helmholtz decomposition, basically means self-organizing systems that attain a or aspire to a non-equilibrium steady state are effectively trying to minimize their self-information. And this can be read in terms of information theory, in terms of the principle of maximum mutual information, or the Infomax principle, equivalently the minimum redundancy principle of Horace Barlow, and in this setting, the free energy principle. In turn, the average of this quantity over time or over a path that I take through state space is known as entropy. So this means that action and perception can also be understood as trying to minimize entropy. And we've just talked about that in terms of resisting a dissipation of my states and keeping them within viable bounds. Of course, if I was a physiologist, this would just be a statement of homeostasis, keeping my essential variables within characteristic ranges that are consistent with the kind of thing that I am. If I was a physicist, this would look a lot like synergetics of the kind induced by Hermann Haken, generalized from laser physics as a nice vehicle to understand self-organization in non-equilibrium. However, there's a fourth interpretation that I want to leverage, and that's the interpretation that a statistician would bring to the table. And she would say, oh, well, this can be interpreted as a probability of some sensory data given me as a model of those data. And in Bayesian statistics, this is known as model evidence, or marginal likelihood, having marginalized away all the causes of the sensory sector of my Markov blanket, namely the external states that are generating my sensations. So what these equations are effectively saying is, it looks as if I am always going to be trying to maximize the evidence for my model of the causes of my sensations. And of course, that's just a statement of the Bayesian brain hypothesis. You can also read this in terms of evidence accumulation, and as we'll see later, predictive coding. So before we turn to predictive coding as an instance of this self-evidencing or evidence maximizing interpretation of the Helmholtz decomposition, I just want to give you a numerical example of this sort of self-organization, just to reveal something crucial, which will be the existence of the synchronization between the inside and the outside that is implied by this self-evidencing, or sometimes called Bayesian mechanics, that emerges when you have a Markov blanket in play. So what we have done here is to simulate lots of little interacting macromolecules. We've equipped them with the autonomous dynamics using the Lorentz system and strong repulsion and weak electrochemical attraction, just to introduce distributed and autonomous dynamics. And here we've color-coded the various states of these little macromolecules as they bubble away at the bottom of some potential well. And you may be asking, well, why have I done that? Well, I can now ask a key question. Is it the case that the internal states look as if they're accumulating evidence or complying with this Bayesian mechanics interpretation of the Helmholtz dynamics. In other words, do they appear to infer the causes of their sensory states, namely the external states? And the reason that I can answer that question is because I wrote down the equations of motion of those little molecules or particles. I can now identify some set of internal states, and then given the definition of the Markov blanket, I can then work out their parents and the children, the parents and the children, to identify the active states in red that surround the internal states that are underneath the sensory states that are pushed out into or exposed to the external states, the external milieu here. And now I want to ask, is there anything characteristic about the internal states in relation to the external states that is an emergent property of this kind of self-organization? And indeed there is, as you might imagine, under this statistician's view of self-organization, what we are looking for is effectively the ability to predict what's going on the outside, given just what's going on the inside in terms of the internal states. So what we've done here is pick out mixtures of the internal states that can predict motion on the outside, say like visual motion, basically motion of the external particles or molecules as they are ejected from this soup and then are pulled back in again. And what I'm showing here is in the solid blue line are the predictions of the motion of the external states. And those external states are given by the cyan, the light blue lines. And what we see is that what's actually happening on the outside lies comfortably within the 90% Bayesian credible intervals based just upon the inside. Remembering, of course, because of the Markov blanket, these states can never be directly affected by these states. So in this sense, you can say that these internal states are somehow representing or inferring the dynamics of what's going on outside, the dynamics that are causing the sensory states that drive changes in these internal states. Two interesting aspects of this, if I just rearrange or time lock these fluctuations to the peaks of the excursion of the external states and the internal states and put them on top of each other, we have something that looks very much like empirical observations from neuronal dynamics referred to as event-related potential. So this is an example from monkey electrophysiology, showing us a remarkable formal similarity between neuronal dynamics and these dynamics of the internal states under this Helmholtzian flow. The other interesting thing is that because of this coupling that is a necessary property of the Bayesian mechanics that arises from the existence of a Markov blanket, if I now plot the most likely internal and external states against each other, what we see is effectively the emergence of a manifold, technically a synchronization manifold. There now is a synchronization or a coupling between the inside and the outside that have this mathematical expression of a synchronization manifold. And this has been well known for centuries now. And what we are seeing is an instance of something called generalized synchronization, also known as synchronization of chaos, that was noted by Christian Huygens in his famous observation that clocks suspended from the same beam or wall will ultimately come to swing in synchrony. And indeed, here's a drawing from Huygens here with a beam and a pendulum here and a pendulum there. And from our point of view, we can associate one of these clocks with the internal states and the other clock as an external state. and the beam as the Markov blanket comprising the active and sensory states. And I repeat, the key observation here is that the only solution in the fullness of time, given that these two systems are sparsely coupled through the beam, or from our point of view, the Markov blanket, then they have to occupy a joint attractor with a synchronization manifold. That means that they come to evince this kind of synchrony. The other nice thing about this drawing is it shows you it's completely symmetrical. So if you subscribe to this view that I am making sense of the outside world by synchronizing with it, then it also means the outside world is making sense of me and learning about me by synchronizing with me. Max.
Yeah, thank you very much. This is super exciting because it sort of like provides a sort of like hypothetical, really simple explanation for something that is a sort of like deep riddle, right? One of the questions that when we look at the brain is that, okay, so neuronal activity firing happens very slowly. There needs to be much more going on. And now the question is, as we look at this, is it just major events where you say, okay, now these two clocks in the case of Huygens are synchronized, and they either do work together or sort of in synchrony or against each other? Or is there also something possible that is sort of like less, say, explicit, less digital, less like more happening in the flow, basically, so to speak? So can there be sort of non-firing synchronization, like in a, I don't know, Kuromoto model where oscillators have maybe even different frequencies and whatever? So in other words, is it possible there's much more going on than just the dynamics of the peaks that you have shown in the last plot here?
Yeah, no, absolutely. And in a sense, it is a synchronization of the dynamics. It's not just the peaks. I just picked out the peaks just to show how experimentally or empirically one might sometimes characterize this kind of synchronization. But the very existence of this synchronization manifold, which is a continuous object, says you're absolutely right. That at every frequency and every scale, there's some lawful probability where there is a synchrony or a harmony between the inside or the outside. That is a very nonlinear one, and it can change with time. And we'll see an example of that in the last slide. So you can choose which part of the world to synchronize with, but what you have to synchronize with something. Just otherwise, you would be violating the solution to this master equation or Fokker-Planck equation, and you would not be basically on your pullback attractor. You would be in some uncharacteristic, very surprised or surprising state. So yeah, at every scale. So you could look at this in terms of sort of fast gamma oscillations in visually induced gamma, or you could look at exactly the same mathematics in terms of natural language processing, fluctuations in some the prosody, the representations of the prosody of, say, spoken language at a much slower time scale. You could even start to think about this in terms of interactive inference and dyadic exchanges in terms of synchronization, both in terms of dyadic interactions and also in terms of populations of people doing this. As soon as you can, mathematically speaking, as soon as you can draw a Markov boundary around something and call it's one of those, then in principle, if it's one of those for a non-trivial amount of time, there has to be some synchronization manifold that emerges from the very existence of the Markov blanket.
And may I ask, I think I've missed one point somewhere. How exactly the Markov blanket is defined in this particular example?
So how exactly is the Markov blanket defined in this particular example?
Right. Again, excellent question. It's defined simply by the normal definitions that arise from knowing the influence diagram or what states are coupled to what. So, and because I wrote down the physics of this little system, I've written down the differential equations for all the states of this system. And because I've written down the differential equations, I know which states influence each other states through the equations of motion. If I know that, I can write down a dynamical adjacency matrix. And if I just identify a subset of internal states, I can then easily compute from the adjacency matrix the parents, the children, and the parents of the children. And that gives me my my Markov blanket.
Am I right that we are talking about some physical, some chemical time kinetics model?
Yes. So in this particular,
so what is the chemical meaning sort of this?
Right, so you can interpret this in many ways. I provided one explanation for these differential equations. So the differential equations can be interpreted in terms of a strong repulsive force. So writing down the differential equations, the kinetics, as you say, one can interpret this as when two molecules get too close together, they're pushed apart. But there's also a weak electrochemical attraction where the electrochemical state of each of these molecules was described by a simple Lorentz system. It can be very arbitrary. This kind of behavior, provided you get the time constants and the amplitude of the random fluctuations in the right range, emerges as soon as you put a number of nonlinear but sparsely coupled differential equations together. And they could come from kinetics, they could come from neural mass models, Kuramoto models, for example, was mentioned earlier on. You could even apply this to things like generalized Lotka-Volterra systems using predator-prey or evolutionary theoretical biology and evolution. As long as the dynamics are sufficiently expressive, i.e. non-linear, and you have the sparse coupling that supports one or more Markov blankets, then you get this kind of behavior. It's another good question because there's not just one Markov blanket. There are an extremely large number of Markov blankets. So for any subset of these states here, then there will be a Markov blanket simply because of the way I've constructed these sparsely coupled differential equations. One interesting point here is that the sparsity inherits from the fact that most interactions in the physical world are local. So that there is no spooky action at a distance in the classical physics, which means that I can only influence my neighbors and not my non-neighbors. And because there are many more non-neighbors than there are neighbors, when I write down the adjacency matrix, it's very sparse. And it's that sparsity that enables the emergence of these Markov blankets. And there's some really interesting work by people, by my colleague Dalton, showing that Markov blankets will emerge with probability 1 in a sufficiently large, sparsely coupled system. Does that clarify things? I've engineered this system so I know where the Markov blanket is. Normally you wouldn't, and you'd have to actually work out the coupling matrix or the adjacency matrix on the basis of the statistics and the dependencies between the various components of the system, and then you could apply the technology that or the analysis that I've just described.
Thank you.
Right. So in fact, that's a nice break point. Maximilian, you're going to have to stop me talking when you want to stop me talking, because I do realise that we've got a little bit sidetracked by the interesting physics of this. But then the second, and I'll try and go through this quickly, the second half of the talk effectively tries to tell the same story, but not using physics, but using the kind of concepts and language that one would use if you were lecturing, say, psychology students or neurobiologists. So I'm going to talk about exactly the same thing, but now from a different perspective, and try to motivate a predictive coding model of this this kind of self-evidencing and Bayesian mechanics, and then finally just illustrate it in the service of two birds synchronizing and communicating with each other. So the story, the narrative from this more biologically inspired interpretation of Bayesian mechanics, sometimes called active inference, could be traced back to the students of Plato. I'm starting here with the 16th century oil painter, famed for painting still lives that, when viewed from a different perspective, give you a very different visual impression. So if previously you saw a bowl of fruit and now you see a face, the point he's making here is that you made that face. This is something that you have brought to the table to explain this particular pattern of sensory impressions. Speaking to the notion that the brain, or the inside, the internal states of any system, can be read as a very constructive machine, a possibly statistical machine, a machine of inference or dynamics of inference, that just tries to find the best explanation for the sensory impressions. And that notion, I think, is probably most beautifully expressed by Helmholtz. So, for example, objects are always imagined as being present in the field of vision, as would have to be there in order to produce the same impression on the nervous mechanism. And again, what it's saying, you have to have it in mind in order to offer it up as an explanation for this particular pattern of sensory impressions. Was this caused by one of those, or was it caused by one of those? And if you've got the right explanation, then you should be able to explain everything that you're actually sensing, even if you don't have direct access to its causes, the external states. And clearly, that idea is very closely related to the notions of perception as hypothesis testing by Richard Gregory, ideas which have been used to great effect in machine learning and artificial intelligence research. So, for example, Geoffrey Hinton and Peter Dayan actually built a Helmholtz machine as a metaphor for the Bayesian brain, borrowing from Bayesian probability theory, and in particular formulated in terms of Feynman's variational free energy, which is where the free energy principle comes from, rendering a very difficult inference or Bayesian problem tractable through the use of these evidence bounds. But let's come back to the notion of impressions on the nervous system. So we can read these impressions really as the external causes impressing themselves on the sensory sector of my Markov blanket. And if this Bayesian view, this self-evidencing view is correct, what that means is I can understand myself on the inside as trying to find explanations for what caused this particular sensory impression, this shadow on my sensory blanket or my sensory veil. You know, was it a bird or was it a leaf? And one can then ask, well, how would the brain do this, or how would neuronal dynamics underwrite this kind of sense making? And of course, we know the answer because the brain has a Markov blanket with its sensory and active state, so it must conform to this Helmholtz decomposition of a flow, and I've replaced the surprisal with its free energy bound here. And if I make the simple assumption that the internal states encode the parameters of some Bayesian beliefs or probability distribution about or over the external states, the causes of my sensations, and assume that it has a Gaussian form with a mean and a covariance, then I've basically now got the functional form for neuronal dynamics. I know that their general form has to conform to this Helmholtz decomposition, but I can actually write the solenoidal part as a prediction and the gradient part, the dissipative part, as a gradient flow on the free energy gradients multiplied or weighted by the precision or inverse variance here. And I've written it out like this because if you were an engineer, you'd recognize this as a Kalman filter or a Bayesian filter. So, for example, if we now read the internal brain states as encoding, say, the expectation about the causes, the external states causing my sensations, if I had some expectation about the external states, I could work out how the external states were going to change in the next moment of time, and that would be a prediction of those changes. And then I've got access to sensory data that I can now use to update my estimate of the causes of my sensations on the basis of a precision weighted prediction error. So what is a prediction error? effectively it's just the free energy gradients, but more intuitively, let's imagine I had this sensory impression on my eyes, on my retina, and I had some expectation that it was caused by a howling dog. And if I had a generative model that could generate from this expectation what I would see if I was correct, then I can take the predicted sensation and subtract it from my actual sensation, and the residual is just a prediction error. So the prediction error is just the difference between what I predict I'm going to see and what I'm actually sensing. And then we can use that prediction error, or this equation says that this prediction error is then looks as if it is then updating my beliefs until the prediction error is minimized and I now have a suitable explanation for my sensations. But notice it's only an explanation. I'll never actually know what caused my sensations. In this instance, it wasn't a dog, it was a cat. But I will never know that. As long as I can keep my prediction errors low for this non-trivial amount of time for which I exist, then job done. I just want to foreground the role of this precision, which is very interesting and speaks to one of our early conversations. You'll see why I want to foreground it in the next slide. And the next slide basically says, well, if then, under this simplifying assumption that we can assume our neuronal dynamics encode or parameterize Bayesian beliefs of these of this simple form, it means effectively that I can reduce all the physics of self-organization to a minimization of prediction error. So how can I minimize my prediction error? Well, I can literally change my mind to change my explanation for my sensations to make my predictions more like the sensations. And we can associate that with perception via changing predictions. But there's another way in which I can minimize prediction error. I can act upon the world to solicit sensations that are closer to my predictions. So that casts a picture of action as changing sensations to fulfill predictions. So action and perception are working hand in hand to realize predictions via this minimization of prediction error, or that is how it looks. What about the precision? Well, if I want to minimize prediction error, what should I do? Should I change my mind and find a different explanation for these sensations? Or should I change where I'm looking or what I'm looking at or how I'm palpating something in order to get a view that renders my sensations more consistent with what I predicted I would see? Would I change the world to make it conform to my predictions, or would I change my predictions to make it conform to the sensory impressions from the world? And interestingly, the way in which you balance these two ways of minimizing prediction error depends very much upon how much weight you afford the prediction errors that are driving your perception. And that weighting is indeed the precision that we were talking about previously, that can be increased in the sense of sensory attenuation, selective attention, or it can be decreased and attenuated in order to, if you like, allow action to actually minimize my prediction errors. So I'll just give you a simple example of that, a numerical example. So what I've done here is I've written out those predictive coding equations or Kalman filtering equations, which are a special case of this Helmholtz flow, and their neuronal implementation in terms of neuronal populations. And I've done so for a song, the bird of a song brain. So here what we can imagine is that some sensations come in from the bird's ear, they enter the auditory thalamus, they are initially not predicted, but suddenly the prediction errors, which are just the sensations in the absence of any predictions, drive changes according to our equation here, our predictive coding equation here, so that the top-down predictions now provide a better explanation for the input and effectively explains it away and eliminates the prediction error until it's driven to suitably low values. And of course, exactly the same mechanism is repeated in a hierarchical way, that I've now got, excuse me, I've now got expectations here that are in receipt of some other top-down predictions. So I now have a secondary prediction error that I can use to then drive changes in my high-order representation, and so on to any hierarchical depth. But notice there's another way in which I can use my predictions, because if I can actually generate a song, if I can sing a song, and I'm now generating the consequences of singing a song, I can also generate the predictions of how I might use my voice box, my proprioceptive predictions. And this is where action gets into the game, because if I can generate what I would expect to feel from my voice box in terms of the consequences of actually moving and articulating and singing, for example, a song, then I can use action to make those predictions come true simply by contracting my muscles to provide the right kinds of proprioception. So this is an illustration of an active resolution of your prediction errors in a very, very simple way, simply by using classical reflexes. So we're not saying that we act in order to bring about visual or emotional or interoceptive predictions. We're just saying that we can use our muscles to bring about or to realize via prediction error minimization proprioceptive predictions, and we can do it in a context sensitive way. So what do I mean by that? Well, in this graphic, I've encoded the precision as being caused by some subcortical input that's assigning precision to the exteroceptive or the auditory prediction errors. So when listening to music, I'm allowing my auditory prediction errors to drive my belief updates, but I've attenuated the precision of any prediction errors associated with my proprioception or with my action or with my movement. And this would be perfectly apt for listening to something. But what would happen if I now attenuated the auditory but enabled the precision of these prediction errors that drive action? Well, now I will reflexively engage action and I'll start singing. But I'm using exactly the same generative model to do both for singing and listening. The only difference is, where do I deploy my precision? And on this view, we now have a nice model of a distinction between, say, motor commands as proprioceptive predictions that can be realized reflexively, and corollary discharge that are basically the exteroceptive predictions that are used during listening. And the balance just depends upon whether I am attending by increasing the sensory precision in the exteroceptive domain, or whether I'm engaging sensory attenuation in order to let the prediction errors drive my muscles to produce the same sensations. It's only that I'm actually producing these sensations as opposed to, say, another bird producing these sensations. So I've gone through that in some detail because I need it to demonstrate communication. So the very last part of this is basically a demonstration of.
Can I ask a question in between?
Oh, sorry, absolutely.
Can I go back? Yeah, so there is there's one sort of like elephant in the room, which is this is a fairly sort of simple interaction model if you draw it as a diagram, even though there's, you know, difficult equations behind it. If we think about Helmholtz thinking that, you know, sort of like the representation is symbolic, so obviously we don't have the wine glass in our head, a la Fechner. So there is some kind of translation going on between sort of the real world and something that is more simple in the brain, say. Now, one of the, like, here's the elephant, like you talk about the synchronization manifold, and one of the key questions could be, is like, how multidimensional is that? And in some sense, like what I'm going to go after is, could it be that, so by what I just said, like this imagination must be sort of like much more simple, meaning incomplete, meaning not the same thing as, I don't know, the vibrating, like if I make a sound that mimics the noise of a forest and wind, I'm not the forest and wind, but I do this in a more simple way, basically, right? And now one of the interesting thing is like, how does that big system sort of like do this kind of simulation? Like, how is my synchronization manifold multidimensional, subject to multidimensional flow? And then, like, you know, we don't even know how fluid dynamics works in 3 dimensions. And so obviously it seems like there's a complex, complicated instrument that we perform as humans, which we don't understand by itself, but it nevertheless works. So we can play the instrument in a sense of perception and action, while we're not understanding sort of like all the dynamics that go on there. So your model sort of like is sort of like describing that kind of process. And like here, I think, I don't know how to put this in a meaningful question. Maybe how multidimensional is the synchronization manifold? Maybe that's a good angle. Does it make sense?
Yes, no, absolutely. That's a great question. Again, you could it could depend upon the scale at which you want to coarse grain the system, but you know, technically it would be extremely high dimensional if established at the level of the Markov blanket, or the inputs and outputs between you as an agent and the rest of the universe, and well, the proximal universe that provides your sensations. So that's going to be extremely high dimensional. I mean, just, you know, and would effectively be the number of photoreceptors and every other sensory receptor in your body, which, you know, would be sort of, you know, billions, or if not millions. So this would be extremely high dimensional, but of course, the whole point about having this kind of hierarchical generative model that is trying to now predict and explain this extremely high dimensional synchronization manifold or sensory manifold is to successively coarse grain, refine, abstract, symbolize, quantize the best explanation for the relevant dimensions of this extremely high dimensional manifold. So I think the answer to your question, how would you frame, articulate, understand this kind of compression into something that we can think about in terms of I am in a forest, or, you know, and communicate that through language, for example, is exactly this the purpose of deep generative models. And a more general answer, I think, is what to your question is, well, it depends upon the implicit form of your generative model of the world. And almost invariably in most interesting simulations and theories, these models are deep in the sense they have a deep hierarchical structure. And each level or scale of the hierarchy effectively does a state space and a temporal coarse graining and dimension reduction, so that you are successively refining, abstracting, and usually, interestingly, making more discrete and quantized your representations, until ultimately you might get to sort of a neurosymbolic or linguistic kind of representation with discrete transition dynamics. One way of looking at this successively deep sort of coarse graining and contextualization is that you are basically trying to compress this high dimensional synchronization manifold that has the same dimensionality as a number of receptors you have available into some low dimensional manifold that you can possibly talk about and even be aware of. And that basically is, when you look at the maths of maximizing the model evidence or minimizing the free energy, that's basically the job of finding the most accurate account of this very high dimensional structure that is minimally complex. And by complex, I mean that you want to use as few degrees of freedom as possible, or put another way, from the point of view of Bayesian mechanics, to move your posterior beliefs as little as possible away from your prior beliefs in order to create that accurate account. So we're talking about Occam's principle. If you're a physicist, it will be James's maximum entropy principle.
Mm-hmm.
Practically or intuitively, what it means is you are trying to compress as efficiently as possible all the information in your sensorium with as little loss of information as possible in order to maximize the evidence in those data or that sensory data for your compressed model of the world. And that compression can be viewed as a successive refinement and carving nature at its joints, but also merging and coarse graining as you go. So, in my experience with simulating these things, you start off with very sort of high dimensional continuous data. And as you get deeper and deeper into the hierarchy, you move more and more to sort of discrete representations that now have the look and feel of a symbolic representation. And these updates, these predictive codings, now have the shape much more of abductive logic, and you start to work more and more with logical operators. It's the same free energy minimizing dynamics, but it's just you're dealing with very precise, discrete representations that you've effectively obtained by this recursive predictive coding scheme in a very, very deep generative model. So to summarize, I think the answer to your question is that the dimensionality of these latent state spaces is defined by the structure of your generative model. And that can have incredible depth in terms of the number of hierarchical levels, but also an incredible breadth in terms of the number of factors that you've carved nature at its joints into, and also a temporal depth in the sense that very often you'd be rolling out into the future when doing planning as inference. I haven't illustrated any of this here, but in realistic simulations of, so say, psychophysics or choice behavior, you not only have a model that just predicts your proprioception, you have a model of the world conditioned upon different courses of action of a much more deliberative or propositional sort. And then you choose the model or the course of action that leads to the least surprising states. And that itself then has some interesting aspects, and you can actually carve it into complexity and accuracy in terms of risk and ambiguity, and it has some epistemic aspects. So it's all about the generative model.
Okay, we got two more questions, one by Pia.
Hi, Karl. This is Pia Tikka. Yes, thank you. This is super interesting. So my background is not in physics, so but I've been following your work so I have a couple actually like a question that comes more from the enactive cognitive science side and more from psychology, cognitive psychology side, which is like. I realized that when you talk about the predictive models and perception action loops, etc., and prediction errors, but you don't use the word cognition. And I'm wondering if actually this prediction process, prediction models and prediction error is a synonym for what psychologists use when they refer to cognition. I was wondering if you would like to open up this a little bit.
Right, that's an interesting question. I've never been asked that before. I mean, you're absolutely right. I don't use the word cognition, but in a sense, I think sort of perceiving your percepts is cognition, and certainly when those percepts have consequences in terms of actions, it will be difficult not to call it cognition. However, I think a technical answer to your question would rest upon what we were just discussing, which is the when doing simulations of this sort, there is a bright line between simulations in which you can engineer reflexes to fulfill predictions, and that's what I was going to show in terms of birdsong, one bird singing to another bird and being able to recognize each other because they shared a generative model. As opposed to something which gives you a much richer kind of generative model, where now the generative model is a model of the consequences of action, which means you can run out into the future, which means that now you're dealing with a much more expressive kind of generative model. And I think that will probably be more apt to describe sort of higher order cognition and cognitive processes, such as attention, for example. And I'm not talking about exogenous attention, I'm talking about endogenous attention. I am now going to act in a way that I'm going to increase the precision to this modality, or I'm going to look over there in the future. So I have to be able to model the consequences of doing that before I choose this particular plan or that particular plan. In order to do that, I have to have a generative model of what would happen if I did that. And so most of this discrete states-based modeling, which moves a little bit away from predictive coding into something called belief propagation and variational message passing, deals with this prospective future pointing aspect. And now you genuinely can now start to talk about the cognitive processes that underlie deliberative behavior, because you are moving out into the modeling the future, a few or possibly many time steps ahead in your head, working out what would happen if I did that, and then evaluating the likelihood that I would do this on the basis of the expected free energy or the expected surprise that actually turns out to be uncertainty, and then selecting the particular plan that you want to commit to, so that then you can then send your predictions to your reflexes in order to do the next thing en route in this in this plan. I would argue that that's probably much closer to the kind of cognition you're talking about. It's one embodied. It has to be acted upon ultimately, and it is quintessentially agentic. There's an agency in play, because the agent is acting and there are consequences of her action. Whereas you could argue this kind of formalism you could also apply to a thermostat. It's just keeping its temperature within viable bounds reflexively by turning on the radiator. I mean, obviously this is a much more glorious and entertaining simulation, but it's just a smart thermostat. So does it have cognition? I mean, you could argue there's a kind of cognition going on here, but it's very, very elemental. But I think when you move to planning, some people refer to this as planning as inference. So when we talk about active inference, we sort of assume we're actually talking about this much richer world. And I think then I think then you'd be in the world of cognition. Is that what you had in mind?
Thank you. That was a very good reply. Yes. So basically, because well, it also relates a little bit to what Max asked about the complexity and holistic way how organisms interact with the world, and kind of this allostasis stages, trying to adapt to the world, etc. So, but yeah, thanks. That was interesting.
Do we have time? We'll make it quick.
Yeah, we do have time. Speak up a little bit.
I wanted to ask, perhaps in this way, that I'll try to briefly explain how I understood what you're talking about, and maybe you can say if I got it. The way I see this filtering system right now is as it's a simple, elegant formation, and which also feels a little bit intuitive to how we perceive things, or at least we think we perceive things. This example of these images where from one angle, you see fruit, and but if you look at it again, you can see a face, right? So it does feel often that we construct our internal world almost in a utilitarian way to make sense of the outer world. But this is now like in a more philosophical layer, and the mathematical tool that seems to help exemplify this is this Bayesian filtering. Is that so far correct?
Yes, no, absolutely. Yeah.
Right. So, and then I guess my question here is, you speak separately about the perception and how like a momentary perception evokes also some sort of prediction for sort of the next stimulus data. And then you speak about action somehow differently. I don't think I entirely follow why and how you make sort of action in the same system different than the perception part. It seems to me that they are the one and the same, because if I'm singing, I have the melody in my head, and I correct my voice if I am wrong. But if I'm listening to the song, yeah, I'm expecting the melody notes to come in, and sometimes maybe they change, and I realize the pianist made a mistake. It seems to me that the model underlying is the same, and the difference is of a much more substantial level that is irrespective of this model. But for me, it seems like you're saying that there is a fundamental model component to these things.
Yes. If you were referring to the last conversation, then I think there is a distinction between this Bayesian filtering account of action, which is all effectively in the moment. So when people talk about predictive coding, they don't mean predictions of the future of an anticipatory or prospective sort. They mean predictions of what I would see in the moment now if I was correct. So it's basically predicting the current input. I should qualify that by saying it's not just the current input, but the way it's changing, but it's usually in the moment. So some people call that merely reflexive active inference, to emphasize the fact that there's no anticipatory or forward pointing or future pointing aspect. And I would argue that it's not really cognitive. It's the kind of processing that you would see in a virus, the kind of processing you would see in, say, many insects. That you're just having the right kind of generative model wired in such a way to do this kind of predictive, this kind of Bayesian filtering or predictive coding, supplying sufficient endpoints or set points to drive reflexes would be a perfectly good account of this, of many elemental, very simple kinds of behavior. If you want to then move up to the next level, then you start to think effectively about how would you plan. And planning provides now, I think, a better perspective on what you were hinting about, which is the prospective aspect of prediction, predicting what would happen in the future if I did this. So now you're in the world of predictions about counterfactuals that have not yet happened. And that's mathematically, and both philosophically and mathematically, really important.
Okay, yes, thank you. That clarified it. Thank you.
Yeah.
I was asked regarding time. I think so. I think it's great. We're on a roll. So there's 2 more questions in the room, and
There were some.
I think we have 45 minutes, so we can. I think we can do these 2 questions, I guess, right? Okay. I have a question which is like directly related. Is that okay?
Yeah.
Okay. So you just brought up, in the moment when I wrote down my question, you brought up viruses, which are an absolute bonkers cool example for this, because they enter the cell and then there is no, there is no inside outside between virus and cell. They become a part of the cell and then they produce more viruses. So my question here is like, and it is even sort of like an extension. It's not only perception and action that are the same thing, or like Eric Kandel would say, made up of distinct bits of information that are sort of the same thing. But it's also the inside outside, where one can actually ask the question, how orthogonal is that actually? And, there's David Krakauer and Jessica Fluck have this new theory on individuality, which emerges on different levels and stuff like that. So you're a human, but you're also part of society, and your cells have an individuality while being part of yourself and stuff like that. So one of the uncanny things, and obviously you don't need to fully answer it, but you present your simulation in a world where perception and action are sort of like separatable, at least in, sort of like time, maybe. The inside and outside is a premise of the model of your sort of Markovian blanket, but what if the real world is actually made up of, and now let's use like words of Leibniz, like of monads, which are not orthogonal, that are not inside outside, but there is some kind of like, not even just a permeability, but maybe a gradient. I don't know. It's like, what's the flock of starlings anyway, for example? So how do we deal with that?
Right. So again, great question. So many ways to approach this. how I deal with that and how many people deal with it. So there's quite a large literature exactly on flocks, for example. So I remember before I say, if you can name it, it is a thing. If it's a thing, it has to have a Markov blanket. Otherwise, you wouldn't be able to name it as something that's separate from everything. So a flock certainly has a Markov blanket for the duration of the existence of that flock. And then you start to ask yourself, well, could I now assign individual birds in that flock to either sensory or active or internal states? And yes, you can. So the interior of a flock, which is only taking information from its neighbors, let's take for a slightly more, I think, sort of plausible example, which is a swarm of fish. So if I'm on the inside of a shoal or a swarm, and I am only able to perceive where my neighbors are going, then I will be an internal fish, so I'll be an internal state to the Markov blanket of the shoal. Whereas if I'm at the head or at the side, at the periphery, then I would be a part of the Markov blanket of that shoal. So that example, in fact, there was a recent paper by Connor Hines, who applies active inference to sort of collective behavior and animal behavior and swarm behavior. I think it's in PNS, it actually deals explicitly and actually interestingly uses this predictive coding mechanics to explain swarm behavior or shoal behavior in fish in terms of their collective decision making. I think what you've brought to the table here is the Markov blanket partition is itself scale free, and you can have Markov blankets of Markov blankets of Markov blankets of Markov blankets, and as such you can then go from the cell to the organ to the person to the family to the population to the and as far as you want. As long as at every stage you can actually name the kind of thing that has characteristic states, which means it must have a Markov blanket. So you can have Markov blankets of Markov blankets of Markov blankets in exactly the scale-free sense that we were talking about before, and they all should comply with this basic mechanics. Interestingly, not all scales have the capacity to do the planning, though. Very small things don't plan, and very big things like the weather or Gaia don't plan. So the planning seems to be sort of a privileged scale, intermediate between there being no random fluctuations and there being your universe being dominated by random fluctuations. So there appears to be a Goldilocks regime, which is basically a biotic self-organization that does support planning, but most of the descriptions of self-organization for things that are much smaller, like viruses and single cells, and things that are much bigger, like population, geopolitical dynamics, the weather, meteorology, they don't need the planning part, so they're sort of merely reflexive in the way that homeostatic, for example, general or homeoretic. But in that intermediate regime, then absolutely this selfhood or individuality is just the mathematical description of self or an individual, or what makes you an individual is the Markov blanket. I don't think you could argue around that. Mathematically, I'm sure you could philosophically, but mathematically, it'd be extremely difficult to imagine anything that could not be separated from everything else. So the Markov blanket, is the definition of a certain elemental kind of selfhood, but it is not unique and it is scale free. And an interesting example is the fact that in those deep models that we were talking about that sort of finesse the dimensionality question that you asked before, the very hierarchy that equips the model with the characteristic or attribute of depth is just a cascade of Markov blankets. So even in our head, at the level of brain stuff and cognition, there are Markov blankets within Markov blankets within Markov blankets. So every level can be construed as having its own Markov blanket. And then you start to ask yourself, well, what does it mean to act? If I'm now talking about a Markov blanket in my hippocampus, what does it mean to act on the larger world, which is just the rest of the brain? And that action is sometimes construed in terms of mental action. And in particular, coming back to the the focus on precision, mental action as evinced by things like selective attention, sensory attenuation. So we can still act on the inside, through Markov blankets on the inside, in a way which I think now is undeniably cognitive in nature, because it's all about selectively attending to this or that, or attenuating basically the complement of attention, which is ignoring this or ignoring that. So you could argue there are lots of selves on the inside as well as on the outside. Is that what you were driving on? There are some
very inspiring and interesting, really cool. This is, I mean, obviously this question probably may not be answered in our lifetimes, but I think it's like that whole notion that there is scale freeness. But what I was sort of asking was like, what if that even that kind of discreteness dissolves, where you can sort of like name the Markov blanket, where sort of the constituents of the Markov blanket may be part of like two different competing Markov blankets, so to speak, if that makes sense. But well, I think we should give the next question to Mauri.
Max, you asked basically the same question I was going to.
Okay, sorry.
Essentially, I was going to use some other words, but I don't have to
thank you.
Do another question.
Okay, this happens more than once with Mauri. It's great. Okay, yes, awesome. Okay, then we can just continue with the talk.
Right. I can't really say. I imagine that if you'd been allowed to continue your question, or your colleague, so yeah, what happens when you eat food, for example, or you cut your toenails? Are these Markov blankets immutable? And of course they're not. Can they move? And the famous example is a candle flame. Does a candle flame have a Markov blanket, in the sense that the plasma around the flame itself is constantly in flux? So this is a really interesting mathematical question, sometimes addressed in the context of wandering sets, in the sense of Birkhoff, mathematical sets. But it does raise interesting question, how transmutable and how dynamic are the Markov blankets themselves. And I think it's worthwhile just saying, again, this is not much help philosophically, but it certainly is useful mathematically, that the Markov blanket is itself a random variable. So it is not a deterministic variable, because it's defined in terms of conditional dependencies under random dynamical systems. It itself is a random variable. So there's plenty of room, I think, to ask questions about how random does it have to be before it can qualify as a random variable. So people like Jeff Beck are doing some interesting work at the moment about sort of discovering Markov blankets, and Markov blankets that can move, like a wave, for example. A wave is a thing, and yet it is constituted by different elements as it progresses through a medium. So I think there's some really interesting philosophical questions about the dynamics of Markov blankets in and of themselves, even at any one scale, which are not fully resolved mathematically. As I say, I normally respond to questions of that sort by saying, well, for a suitably short period of time, we can ignore that, and we'll assume that we've actually attained a quasi non-equilibrium steady state, and then we'll move to another one at a different, in the next period of time. But there may well be a maths and a philosophy of dynamics of blankets in and of themselves, which would be really interesting.
Cool. We got another 35 minutes, so maybe just continue with your talk, and then,
right.
Okay.
Well,
thank you.
I was enjoying the questions, but let's get back to the talk. Right, so we just established a slight sort of, well, as we've just seen in terms of the discussion, quite an important aspect of this kind of Bayesian filtering or self-evidencing, which is the encoding of not just the content in terms of expected states of affairs out there, but the context in terms of the amplitude of the random fluctuations, or the certainty, sometimes referred to as the encoding of the uncertainty, in terms of the precision, which is the inverse variance of these random fluctuations. So if you like second order inference, that can play a key role in deciding whether to act or not, or to listen, or to talk, or to sing, or to listen. So more generally, the argument goes like this. It's quite an interesting argument that most of what I do as an autonomous agent rests literally upon autonomous dynamics. And in the example that I was going to show, those autonomous dynamics come from a Lorentz attractor, which is a mathematical expression of an autonomous system. There are no outside inputs, it just does what it does. So this is a famous butterfly attractor that was developed in meteorology. And in generating predictions of the future under this, in this autonomous context, you can read these as basically intentions about what is going to happen in the immediate future, or in terms of the dynamics that is happening now. And if there are intentions, they can be realized by reflexes in the way that we've just described, much like a thermostat or a virus, for example. However, if I don't attenuate the proprioceptive or sensory, any sensory sensation or prediction error in the sensory domain that would otherwise report the fact that I'm not moving as intended, then I will immediately change my mind about the intended movement, which means I have to ignore any evidence that I'm not moving in order to act or to realize a prediction that I am acting. So this in psychophysics is called sensory attenuation. And in this context, it's basically the attenuation of the precision of sensory prediction errors that report the consequences of the action. So it leads to a really interesting notion that in order to do anything, I have to ignore the fact I'm not doing it. And that means whilst I'm actually doing it, or certainly during the initiation of doing something, I'm insensitive to the consequences of my action, so that I will always perceive the self-generated consequences to be lesser than if you generated the actual same sensations. And there are all sorts of interesting arguments, or examples of this kind of sensory attenuation. So it's this precision control is a really important aspect, I think, of cognition under this kind of an elemental sort, under this kind of model. But to come back to the example and why we're going to use sensory attenuation, or why we need to use sensory attenuation for the final demonstration. So what we've done here is actually a nice example of actually composing a deep generative model that has this very coarse graining aspect that we're talking about previously, in terms of compression and boiling down or reducing or abstracting the relevant dimensions or factors that generate our sensorium. Here what we've done is just take a Lorentz attractor that is moving very, very, very slowly. And then we're taking two states and we're plugging them into the parameters, the control parameters of a lower Lorentz attractor that's moving more quickly. And then we're taking these states and we're using them to drive the voice box of a bird. And by doing that, we can actually generate sonograms of time frequency fluctuations. You can't hear it, I can. I'll just play it for my own benefit. They sound very much like a little bird. I won't try and imitate it to you. You'll have to believe me. They sound very much like a little bird chirping away. But because we've equipped it with a deep structure, this is not just a beep, 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 or beep, beep. It actually has deep non-Markovian structure, a little bit like language, because the dynamics are themselves being controlled by another slower chaotic dynamic. So you can imagine doing that at any hierarchical depth required to equip the songs with a deep temporal structure that has this sort of scale invariant aspect that we're discussing with Max earlier on. So we can build one of these little synthetic birds and we can get it to sing a song. And what we did here is build two of these little birds and then ask them to sing together. And the crucial thing we did was to equip both of the birds with the same underlying generative model, these coupled Lorentz attractors with separation of kinetics or tails. So they both knew the same song, but in the first instance, we asked them to sing and listen by switching the sensory attenuating and then augmenting, attenuating and augmenting, just by flipping the precision that we were just talking about before. So those correspond to the blue and the pink lines, and this basically reports the expectations or representations of the causes of the songs at different levels. In the first level of the model, which shows these fast fluctuations as the chirps are emitted and terminated, and these slow fluctuations which set the context, where are you on the attractor manifold in generating these fast fluctuations for the two birds in red and blue. Whilst they were, one of them was singing and the other one was listening, and vice versa. And by the fact that they had exactly the same knowledge and generative model of how to sing this particular song, they could not hear each other, and therefore, due to the sensitivity of initial conditions, they never really represent, i.e. perceive, the same thing. So there's no convergence between the red and the blue. But if I make now one very simple move and bring them together so that they can hear each other, we should be able to evince this generalized synchrony, or literally synchronization of chaos, so that on the inside of the two bird brains, there is now a synchronization. So their internal representation of the song now is synchronized, crucially, whether you're listening or singing. So that means when I'm listening to you, I'm still in my head representing exactly what you are using to generate your song, even though I'm not doing it. But then I will take over, and you will be quiet, and you will be listening to me. But we're both continually pursuing a trajectory on this manifold. There's a shared manifold, as if we're singing from the same hymn sheet. And it's not a simple hymn. It has this sort of deep semi-Markovian structure. But when we bring the two birds together, what we see is now a synchronization. So this is exactly that synchronization manifold, or synchronization of chaos. Now notice that this synchronization is between two birds, simulated neural dynamics in two completely different brains. The only way that they are coupled is through their turn taking of singing and listening. That's the only way, through the actual fast fluctuating sounds that are emitted, that engender this kind of generalized synchrony. So that was my attempt to get to communication via generalized synchrony from first principles. This is the synchronization manifold associated with that particular very elemental kind of communication. It's not quite as elemental as I remembered it, because it does actually, I think, rest upon this notion of turn taking, that I can't talk and listen at the same time. So we have to take turns in communication. But the fond hope is that we're both on the inside pursuing the same narrative and the same, literally, song sheet, so that we could be effectively able to predict and synchronize with what you are going to say next.
There's a question.
Yeah.
If I may, perhaps this is something trivial to the rest, but I wouldn't believe so. Perhaps can you please just highlight or exemplify how this particular synchronization that you derive now from model brains is distinct and more than simply observing stochastic resonance in two coupled oscillatory systems?
In one sense, it's not. In one sense, it's not. Although stochastic resonance has a very particular meaning and is usually associated with sort of threshold crossings in stochastic or random dynamical systems, if read more generally, if you've got a sparsely coupled dynamical system, then you will evince this kind of generalized synchronization of chaos. The key point here is that in virtue of the sparsity, there will exist Markov blankets. And if there exist Markov blankets, you can now interpret that generalized synchronization or synchronization of chaos through the lens of self-evidencing and belief updating, Bayesian belief updating. So I'm not, very often people misinterpret the free energy principle as saying that in order to survive and maintain your Markov blanket, you have to have a good generative model and synchronize with the world. That's not what the free energy principle says. The free energy principle turns that on its head and said, if you exist and survive within this world over a non-trivial amount of time, there exists a description of your internal dynamics that is as if you were actually synchronizing with the world through modeling and predicting that world. So it's somewhat tautological. However, what you can then do is you can then, instead of trying to work out what kind of model this bird is using to understand its world, or this patient or experimental subject is using, you can actually write down a particular model and then just integrate these variational dynamics in terms of the gradient flow, the Helmholtz flow on variational free energy, and then start to simulate and reproduce the kinds of behaviors that you hypothesize are going on inside the head of your patient or your experimental subject or your songbird. So there's nothing remarkable about this. It's just that its existence is remarkable in the sense that it offers an alternative, or offers a relatively straightforward mechanics of belief updating that is now apt to describe lots of things that preoccupy us as neuroscientists or psychologists or psychiatrists.
Maybe I can extend the question. So if this is not just a stochastic resonance of coupled oscillators, then one can extend the model, which you cannot do with coupled oscillators in a Huygens sense, being on the same bar. Let me put it in a very, very snarky way. Like, what came to my mind is Sun Ra, and the question is, like, can chess happen among the two birds by adding just like one source of correlation that one bird has and the other doesn't? So can one improvise about over their synchronized song, which probably doesn't happen with coupled oscillators, but in a bird it could happen. So in a sense, could we add something to the patch of one of the birds to make this more interesting, which in this model should work, while in a coupled oscillator Kuramoto sense it probably doesn't, right? I mean, they don't improvise. They're not active.
They're not very good at playing jazz. Yes, absolutely. And indeed, this very elemental model has been taken in a number of directions. So this was work by my colleague in Japan, who was then addressed how this kind of coding could be contextualized to actually enable who you're talking to, or who's singing at the moment with multiple birds. But I think more interestingly is your question when we don't share the same generative model, and therefore I can't predict you, but I may think you are improvising. And how can I now learn your generative model? And so, although it doesn't address the issues of improvisation, it does bring to the table a really interesting question that when you start to introduce asymmetries between the talker and the listener, or the correspondence of any sort, usually in terms of who has the most precise beliefs, prior beliefs about the way that their narrative should unfold, then the mechanics, the basic mechanics and self-evidencing suggests that what happens is that the less confident correspondent, the one with the imprecise priors relative to the more confident or correspondent, will now converge upon the generative model of the of the more precise, more confident one. So you get basically a sort of student-teacher kind of relationship that can be quantified exactly in terms of the precision with which you equip the autonomous dynamics that could be deeply structured, that say, this is how this person, teacher, bird, politician thinks the narrative should unfold, and then the younger or the less wise or less precise people tend to follow. So some really interesting questions you can use to actually think about beyond communication and now how one can learn a particular language. And then you move on to issues, well, issues that you were hinting at before in terms of, well, this is fine just for producing songs, and it might be nice to simulate people singing in the same choir or perhaps dancing in the same dance group. But is this really communication? Is this belief sharing about something? And of course, it's not. Then you move into the realm of what it is to actually semantically label and converse when you're both looking at and experiencing a shared world, but you also have the opportunity to share your beliefs on the inside through vocalization. How do young things learn to do that? And is that an emergent property? And in fact, it can be. And the answer is actually relatively simple, that if the imperative is to make sense of my world by minimizing expected surprise, then I want to render the world as predictable as possible. And I am compelled to seek out novelty in order to resolve uncertainty, to make my world as predictable as possible. One way of making the world predictable is if we all share the same language. And if we all share the same language, as evinced by a mapping between what we believe and what we say, then that should be an emergent property of this sort of joint surprise minimization. And you can simulate that. You can simulate the emergence of a very primitive kind of language where you're talking about your posterior beliefs about states of affairs in the world. And then you get into the interesting game of, well, I've now got two teachers. Who do I believe? And then you start to get into polarization when you have large groups of agents who now have to choose who to listen to. So this sensory attenuation goes beyond attenuating or ignoring evidence that is counter to my prior beliefs in terms of wanting to move. But you can also ignore evidence that would otherwise induce a degree of complexity which you want to minimize to maximize the model evidence. So you're going to ignore stuff that in a Bayes optimal way that obliges you to move your posteriors a long way away from your priors. So you have to actively sort of set this attenuation, which, read in terms of epistemic foraging means you have to choose who to listen to. And that leads to really interesting dynamics when you get, lots of agents trying to resolve their uncertainty by querying themselves, where they have the opportunity to attenuate or to attend to this kind of agent or that kind of agent. And there are some very early sort of simulations of multiple active inference agents, pursuing this and exploring different solutions in terms of polarization, for example, and voting dynamics.
Mm-hmm. Excellent, like super interesting. What comes to my mind regarding what you just said is there is this concept of Kaneko called chaotic itinerance, which seems to happen in the brain where we sort of like loop around certain attractors, but the attractors are actually not attractors, but attractor ruins. And once you exit the attractor, you sort of like can fluctuate system space until you catch some other attractor ruin.
Yes.
And so the question is how like, obviously the attractor situation is sort of interesting and but sort of intuitive, but how do we deal with the fact when we sort of exit the attractor? Like can that be performed too? ?
Well, yeah. So yeah, chaotic itinerancy, I think, and there's another notion promoted by Mikhail Rabinovich, which is sort of stable heteroclinic channels, So, or heteroclinic cycles, where you have a sequence of unstable fixed points that sort of give you a certain kind of itinerancy. So yeah, I think chaotic itinerance and transient chaos and the kind of itinerancy associated with heteroclinic cycles or orbits are all really important ways of describing the kind of pullback attractors upon which all of this maths rests. Absolutely. So I just put this picture up. I think I may have even put itinerancy down as a search for an image of an itinerant attractor. So itinerancy simply read as wandering around, I think captures exactly what you were talking about before, which is a sort of potentially enormous dimensionality of these state spaces. And yet, paradoxically, we seem to occupy a very small volume of what could be an enormously large number of states in a very large number of dimensions that we could occupy. And yet, we seem to visit lots of different parts of this state space in an itinerant fashion, in a wandering peripedantic fashion. So there's this paradoxical structure that is at once space-filling, in the sense that it is quintessentially itinerant. There are many, many ways of being alive, but it is also very small volume, or has low measure, in the sense that there are many fewer ways of being alive than there are ways of being dead, where I don't go. And this sort of low measure, low volume, space-filling aspect is exactly what I was trying to communicate with this graphic, and I think exactly what you mean by chaotic itinerancy and ghost attractors and Milnor attractors that have this aspect. One could. If I'd given this presentation but tried to explain a thermostat, I would have started here with a simple periodic orbit. But I'm not. I'm trying to tell a story about more biotic kinds of itinerant dynamics, but the maths would be exactly the same. So I think it is exactly the itinerant aspect of these attracting sets. One final mathematical qualification: these are pullback attractors, so they're random dynamical systems. So they do not yield to the maths of deterministic systems. So you can't, strictly speaking, talk about Milnor attractors or ghost attractors. They don't really exist in this. This is a random dynamical system, which is so yes, you talk about stochastic chaos as opposed to itinerancy. Part of that sort of itinerancy in this world comes from the random aspect. But there will be another part that inherits directly from the deterministic itinerancy you get from exponential divergence of trajectories and sensitivity to initial conditions and the like. But the phenomenology, I think, is exactly the same.
We got like 13 minutes to go. There is, I have been alerted by, so there's some general questions. Mike Tom has one. Do you want to conclude your talk, or do you take the question right now, or like?
Well, I had got to the last slide, which is the same as the first slide.
Then Mike will give will initiate the general questions. Then let me do this, so we all see each other.
Should I stop sharing now?
Yeah, you can. Let's show the names.
The question was related to picture we had. Just exactly the same page, which was. Am I here well, or should I come closer to Max?
Yeah, I think you should take the blue seat.
Sit here near the microphone. Is it better now?
Sound-wise, yes.
Sound-wise.
Don't take it like.
Can you hear me?
Yes.
Yeah. So basically, I was trying to sort of generally understand the framework, and it seems to me that you are relying very heavily on the fact that you have these non-equilibrium steady states, which are, of course, I mean, given the state of your envelope, the state of your Markov blanket, of course, you probably get in the end of the day to some sort of non-equilibrium steady state. but the relaxation, but then if the surrounding, if the world is changing too fast around me, then the state of the internal degrees of freedom has nothing to do with non-equilibrium steady state corresponding to whatever the surroundings. So it seems like there is something very important going on here in terms of separation of time scales and separation of dynamics on different time scales. And can you maybe sort of speak about it a little bit and explain what are actually your underlying assumptions about that?
Yes, no, that's again another excellent question, and we certainly touched upon that earlier on in terms of the scale-free aspect of applying this kind of maths under the renormalization group, and that separation of temporal scales is absolutely crucial. So, in the context of a recursive or scale-free application, I repeat, under the renormalization group, what you are saying is effectively for a particular period of time at any one scale in my system, I am going to make effectively an adiabatic approximation that the context is changing very, very slowly to the extent that it's not changing, and therefore I can approximate non-equilibrium steady states during the period of time that the parameters or the variables that provide the context are effectively constant. And then you move to the next scale, and then you make the same assumption, but now because you've contracted time, things look as though they're changing much more quickly. So you basically
So for any given sort of problem, like if we're thinking of a internal set of degrees of freedom as a human, say, yes, there are some internal degrees of freedom which are equilibrated with respect to whatever external signal we are talking about, and some of them are evolving. Yes, so in principle, it should be there should be some sense in well for a given task to distinguish between internal degrees which have reached a steady state and internal degrees which are evolving. Or
yes,
am I?
Absolutely. I mean, a nice example of that would be, which we didn't touch upon here, would be using the same gradient flow at different time scales to simulate perceptual inference and action at a very short time scale at the same time as learning at a much slower time scale. So usually, I don't know if I've got an example here, but usually you sort of write down, I haven't got the actuals. Usually the generative model is written down in terms of equations of motion and nonlinear functions that are actually parameterized. Now, these parameters can also be learned by slowly doing a gradient flow on free energy. But of course, the speed at which you're learning, you're evolving the parameters of your generative model, which in the neurosciences would just be the synaptic efficacy or the connection strengths. In machine learning, it'll be the connection weights. So the connection weights change very, very slowly. They're still minimizing the path integral of the free energy, but that on a much slower time scale. And they, of course, contextualize all the fast message passing, the dynamics that does the perception, for example, recognizing a particular song. So I think that was a really nice example that you reminded me of by talking about the evolution of things. So slowly the context is changing as you are learning, and that provides a context which enables you to infer what's going on in the moment. And I repeat that adiabatic approximation, that separation between assumptions about the way that the parameters change very slowly and the way that the states of the latent states or the hidden causes of my sensations change very, very quickly, is operationalized in terms of a mean field factorization between the posterior beliefs about the parameters and the posterior beliefs about the states. So you operationalize that adiabatic approximation with a mean field approximation in exactly the spirit you were talking about. I can't resist also just noting that you can then extend that argument to model selection. So not only do the parameters of a model change very, very slowly as we get older or we learn a new motor skill, for example, but the very structure of the model also changes in terms of building new connections, building new neural populations, or even removing them as we have normal aging or synaptic pruning during adolescence. And that brings to the table this notion of very, very slow optimization, pre-engine minimizing processes, where you choose your very structure or your very model on the basis of the model evidence. So in statistics, that's called Bayesian model selection, selecting the best model or the best structure that has the highest model evidence or the highest marginal likelihood averaged over all the data that you have seen and are likely to see. And of course, that's a nice mathematical metaphor for natural selection. So now lots of people are now looking at natural selection as effectively Bayesian model selection, where you can look at evolution, running experiments where each of us is a hypothesis or a model of what will work in this environment, and then selecting those models that have the greatest evidence or marginal likelihood of being in this environment through the process of natural selection. But of course, this occurs very, very slowly. Within each act of selection, I've had to do all my learning. And within each epoch of learning, I've had to do all my inference or hidden states. So again, speaking nicely to this sort of nesting of separated temporal scales, but all trying to maximize the evidence for effectively the model of the lived world or co-constructed world.
As far as I remember, there was this paper a couple of years ago by Kunin and Katznelson about theory of evolution as multi-level learning or something like this, which is basically rhymes very closely with what you just described.
Excellent.
Yeah, I like to close with take the privilege to ask the last question. We started with Helmholtz, which I'm yeah, I love Hermann von Helmholtz for not just this reason, but many reasons. Here's one of the sort of like key nuts he puts in a chocolate is symbolic cognition, right? So the idea is that the representation in the brain has nothing to do necessarily with whatever's outside, but it's just a symbol of whatever's outside. And so this is like sort of the first half of the question, like how arbitrary can these symbols be? How arbitrary can they be?
Yeah. Well, they clearly cannot be arbitrary from your point of view, in the sense that they are the most parsimonious compression of all the best explanations for this high-dimensional sensorium. If you're asking how arbitrary can they be from the point of view of somebody looking at you and indeed trying to talk to you, I guess they can be completely arbitrary unless you have a shared frame of reference or common ground that allows you to communicate between them. But you know, this is not a philosophical argument. This is just a statistical argument that, you know, if there is lawful structure generating some content or some data, then the way that I would carve that latent nature at its joint statistically into multiple factors that could have a deep hierarchical structure, you should get consistent structures and factorizations out of that, simply because you're trying to find the simplest explanation for these data in terms of their underlying causes. That simplicity, I repeat, inherits from James's principle of maximum entropy through to Occam's principle. It just inherits from the fact that the log of the evidence is equal to accuracy minus complexity. So my job is to find the minimally complex explanation for what could have caused all these sensations now and in the past and in the future. And of course, the best, simplest explanations are going to be a short bag of symbolic representations. That's why you coarse grain. You throw away all the irrelevant stuff and you just have a little bag of simple things. It's one of those, it's one of those, it's one of those.
Excellent. So this is part one of the question, and you arrived exactly thank you very much. So sort of like this symbolic thing that we're thinking of, like the first thing that comes to mind is terminology in humanities, like naming something after something, or make it digital 0, 1, like, am I in danger? Yes, no. Yes, square the ink. No, just sit around on the rock. So this kind of thing is sort of something which seems intuitive, but in the real world, where sort of like, that doesn't come in 3.5-inch floppy disks, and with neat little buckets for 0s and 1s, firing in neurons seems to be hard because otherwise we wouldn't be so slow doing it. But then there is other things happening. Like Wolf Singer would say, oh, these neurons are all analog. And even the receiving neuron after firing is already acting analog. The firing neuron is acting analog when it's not firing. One can imagine there is like oscillations going on at multiple scales of time, like very fast, middle, and was like all happening at the same time. And then, 2 days ago, there was this paper coming out about super radiance. So there may actually be even faster oscillators, quantum level, in any eukaryotic cell, including non-neurons. So if we're in such a situation where oscillating, synchronizing in time seems to be a much simpler process, but hard to imagine than actually coming up with a label and putting something in a nice little box that one can diagonalize on a confusion matrix. Can we imagine maybe a process that does what you describe, but more complicated or complex to explain, but actually more direct, being part of the process of life, which seems to be a multidimensional and a 3-dimensional fluid dynamics problem? Or is that too crazy?
No, I'm not. I'm still thinking about this notion of oscillations and Wolf's focus on oscillations. And I mean, I am very sympathetic to the view that at the level at which we communicate and think about things in a propositional way, that we do think in terms of simple categories and discrete representations that have all the attributes of symbols and semiotics and everything that you would need in order to organize your thoughts about the world and the way it's unfolding. And I would argue that if you look at neuroscience and neurobiology, the brain very, very quickly gets into that space. So yes, you could get visually induced gamma, beautifully induced by Wolf and all his young men that subsequently followed. But notice that they are being produced by classical and extraclassical receptive fields, populations, cells that have a classical receptive field. What does that mean? Well, that means that the brain is already quantized. It's already symbolized. The brain, because what you're saying is that this cell represents some attribute, perceptual attribute, that is here in the receptive field and not there, which means you've already got into a discrete world. So just having, for example, let's take velocity as an example. So V5 or MT cells fire away at gamma. when the say a moving bar has a preferred velocity, usually sort of about 8 degrees per second, for example. So what kind of neural coding is that? What kind of brain representation have you got? You've got a symbolic representation of what I am seeing now is best explained by something that is moving at 8 degrees a second and not at 4 and not at 2 degrees per second. It is not that as the bar moves faster and faster and faster, this population has greater and greater and greater amplitude gamma. It's not like that. So I think there's lots of empirical evidence. As soon as you get to parts of the brain that actually start carving literally nature at its joints in terms of receptive fields, you've already entered a discrete quantal regime. And one of the reasons I was smiling and thinking furiously about oscillations is, of course, it is oscillations that gives you quantum mechanics. Quantum mechanics you can read as effectively a Fourier transform of the that master equation or Fokker-Planck equation read as a time invariant Schrödinger equation. So you can derive all of quantum electrodynamics from the equation I give you if you use oscillations by using the Fourier transform. And put very, very simply, that's where quantum behavior comes from. Because imagine fitting an oscillatory wave on a ring. Now, if the wave has to be continuous everywhere, you can only put 2 wavelengths, 4 wavelengths, 3 wavelengths. You can only put a discrete number of wavelengths, probability distributions, on that ring. So in radial coordinates of motion, which of course is where the coordinate frame that quantum electrodynamics lives. So oscillations as a construct, as a hypothesis or a fantasy, a mathematical fantasy, are what leads to quantum mechanics. So I'm wondering whether one should not really reify oscillations, but really sort of admire our tendency to quantize things. And it's an important thing to be able to do. I mean, that's, I think, why people are so fascinated with quantum computation, because if you can get it down to that level, the operations are so efficient, again, in the sense of eluding complexity costs. This, coarse graining in this kind of way can be so efficient. It's, it will have not just statistical, but also economic and thermodynamic payoffs if you symbolize at the level of quantum mechanics.
Super, super awesome. Thank you very much. This was super inspiring. We're over time. I say the last thing in the last 10 seconds. Atao Tanaka will speak next week. He is a musician speaking about embodied musical interaction, and he's a gestural musician. So this fits right, like sort of, it's a really cool next talk from where we are right now. And yeah, this was amazing. So I'd like to thank the people who suggested you also. I learned a lot. Thank you.
Well, thank you. It's been wonderful talking to you. Thank you for all the questions.
I